Now we'll move on to the next speaker. With us we have Arun Muthukkumaran. Arun Muthukkumaran. Right. I would request Arun Muthukkumaran. I think he's giving his presentation in person. So could you please open the presentation? He's going to talk to us on AI in energy materials discovery and design. Arun, you may start your presentation. You have 7 minutes.
So, good afternoon to everyone present here and also to everyone who is joining online. I'm Arun. I'm a PhD scholar in the Department of Chemical Engineering, working with Professor Raghunathan Rangaswamy. So today I'm gonna present my research on the topic AI for energy materials. So recently we have seen natural language processing and generative models being applied successfully for a large variety of tasks. So in the natural language processing area, we have seen large language models such as Deep GPT and its variants doing pretty successfully in natural language understanding as well as generation. And in generative modeling, we have seen the adversarial network-based GANs and diffusion model-based DALI perform very well, and they have revolutionized image generation and text-to-image synthesis. So in this research, we explore the applicability of natural language processing techniques as well as generative models for design and discovery of materials related to energy applications. So this is the natural language processing methodology that we followed. So the use case here is to identify electrocatalysts for usage in lithium air batteries. So initially we collect a corpus of 7.5 million abstracts, from there we do a couple of pre-processing steps. Then we tokenize the model. We tokenize the corpus and we train the model using, here we used the Cybert language model. So one step here is that the vocabulary of the pre-trained model contains only English words. So we have to add the materials to the vocabulary, and then we get embeddings for the materials of interest. So here the material of interest for us was perovskites. So embeddings are nothing but vectorial representation for words, and in the vector space, materials that have similar properties, the vectors of those materials lie close together. So we use cosine similarities between the application keyword and the material embedding to identify the best materials for that particular application. So once we obtain the perovskite embeddings, we use them for 3 tasks. One is predicting perovskite-based electrocatalysts from literature. This is the materials discovery part. Then synthetic embeddings for perovskite. So this is the material design part, and we followed it up with some property prediction. So here we are predicting electrocatalytic activity. So these are the embeddings, these are the perovskites that we obtained from literature. So these are the top 5 perovskites obtained by taking a cosine similarity with the keyword electrocatalyst. And we also, for validation, we go to literature and we search for the applicability of these materials for electrocatalytic research, and we found that the top 5 materials are all already being used and are very popular in the domain. So the model is predicting materials in a correct way. So the next part is materials design. So here, to design the material, we go with the combinatorial approach. So we look at structures of type AbO3 and then its variants. So for the A side, we have the materials that are commonly used. Then similarly for the B side, and these are the atomic fractions that we used. And we generated 17,290 combinations. So the next task is to screen them for their applicability. But the problem here is these materials are designed and they are not present in literature. So we have to get embeddings for them. So we came up with this methodology, this algorithm to compute embeddings for the materials that we have designed, and we call them as synthetic embeddings. And so this algorithm works based on finding similarities between the perovskite that we designed and the perovskites that have been existing, like that for which we already know the embeddings. So we kind of arrive at a similarity between the synthetic perovskite and all the existing perovskites, and we convert this similarity scores to probability using a softmax function, and the combined embedding or the synthetic embedding for the designed material is sum of the probabilities and all the word embeddings that we have for the existing materials. So the next step is again to validate these materials. So these are the top 10 materials based on again our cosine similarity with the keyword electrocatalyst. So we found that the A site mostly contained lanthanum and the B site had cobalt. So to reduce the amount of, to reduce the candidates and to analyze the materials in a better way, we started looking only at materials with an atomic fraction of 0.5. And when we did that, interestingly we found materials that could substitute for cobalt. So cobalt is a toxic material, and it also has supply chain issues. And the next result was that out of the top 20 materials that the algorithm had predicted, 14 materials were already being used as electrocatalysts, and these materials were identified without any, only through the synthetic embeddings. So this validates our result that, our hypothesis that the synthetic embeddings actually contain knowledge and can be used for materials discovery. So the next task was property prediction. So for this, we created two data sets. So the first data set we created by collecting perovskites and their activities from literature, and we used descriptors or the properties of the material as features to regress for the electrocatalytic activity. And the second data set contained the material embedding along with the descriptors as features, and we found that in the second data set, the root mean square values were pretty low, which suggests that the embeddings are able to impart their knowledge to the regression model, and we are getting better results with them. And the next part is the generation part, where we are trying to predict the crystal structure for these materials. So we are using a GANs model for this, and okay. So the training set is made of CIF files and the data from CIF files, and we are training the GANs model with these structural data for known materials. And once the GANs is trained, we are using the generator, and we are conditioning the generator with the word embeddings, and we are generating the structure for new materials. So since the training is still going on, I'm unable to share the results here. And this is the final algorithm that combines the natural generation NLP part and the generation part. So we have methodology for knowledge assimilation from research papers, and with that we are going and discovering materials and generating their crystal structures. It's not random generation, it's generation with generation guided by NLP. So thank you.
Thank you, Arun. As a token of appreciation and a small memento from IIT for being in person here. Thank you.